Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, my name is Rob Fotland. I'm with the Earth, Energy, and Environment theme within Microsoft Research Connections. And I'm here to introduce our speaker today, who is Ananya Sengupta. And she is a postdoctoral fellow at Woods Hole Oceanographic Institute. And she works in signal processing with a current emphasis on topics in oceanography. The title of her talk is Signal Processing Challenges in Physical Environments. So, Ananya.
Thank you, Dr. Fatland. It's a pleasure to be at Microsoft Research and talk about my research. And I decided before I really jump into it, I'll give a little bit of a synopsis of what I do, how it relates to oceanography, and how it can be of interest to Microsoft or in general the research and development industry. So bear with me for a while. And do I use this? Where is my mouse? No. So I identify myself as a person who has worked with signal processing problems, solving signal processing challenges, and developing novel applied mathematical and statistical techniques wherever there is a signal processing challenge or an application. And I've been doing it, I don't know, since 1999. And the applications has ranged from MRI medical imaging to nonlinear amplifier saturation in satellite communications to shallow water acoustic channel characterization, petroleum fingerprinting, biological model validation, underwater imaging using lasers. So there's a bunch of applications here, but what binds them into one picture to make it interesting as a coherent story? So one day I sat up and looked at all the different things I had worked in, some things pretty deeply, some things more on the superficial level, and I found that what tickles me about signal processing and ultimately got me into ocean sciences is the signal processing theory and principles that we study in our undergrad, and many of us make careers applying them all over the place, do rely on some what I call the, commandments of signal processing, simplifying assumptions that really make the theory and principles robust for a lot of engineering applications. But when we are really pursuing the cutting edge of science, when we are really trying to deal with the real physical environment, biological processes, a lot of natural processes that we do not have any control over, then a lot of these fundamental assumptions get blatantly violated. And then there has been, a whole subgenre of work. And if these assumptions get violated, how do we design the system so we still kind of stay in the house without things getting wild? And I am someone who kind of likes to jump into the snake pit, so to say. So I'm very interested where there is one or more of these fundamental assumptions: linearity, orthogonality, time invariance, high signal to noise ratio. All of these things, one or more, get really hard to sustain. And then the question is, can we build something new? Can we do something different that is not going to be just a solution for the particular problem at hand? It's important to solve the particular problem at hand, but it would be a lot more general. It would be a general extension to signal processing as a field of science itself, so somebody else can take what I develop and run with it on a completely different application. And that's essentially why I'm here as somebody who is now with significant research thrust in oceanography, but trying to talk across the board to Microsoft Research and Development, because I strongly feel some of the problems I look at, some of the science I develop have applicability beyond just the scoped applications. And I hope that I'll hear a lot of you come back and say, oh, we deal with this issue too. And then that gives me a lot more inspiration to develop my techniques that are more general and maybe even strike up interesting collaborations. So with that goal in mind, I'll jump ahead and talk a little bit about my one-line vision of where I think signal processing theory fits in to the world of science, research, and business. And I feel that we can significantly expand our scientific understanding of complex physical environments by breaking the barrier of these limiting assumptions in signal processing theory. Because once we do that, then the mathematics will enable us to just see different things, measure and observe different natural things that will tell us a lot more about our environment. And as we know more about our environment, we can design more novel solutions to get what we want. So with that, what are the short-term goals that I want to address, currently addressing in my work? So it's going to get pretty technical, and it's okay if you don't directly follow every bullet, because I'm going to basically zoom in a couple of them and come out. But these bullets are important as they really tie into the research vision. So the 4 things that are keeping me up at night is equalization and channel estimation for time-varying systems. Specifically for me right now, the shallow water acoustic environment. Sparse sensing for highly conditioned and coherent system. It basically means you have a lot of signals that are overlapping with high coherence, which makes it even harder to separate them. And with some focus where you have a few components that are of much more interest than the rest of the components. And then nonlinear and highly correlated signal separation and optimization in the low SNR and non-Gaussian regime. So these 4 bullets would summarize my different technical thrusts at this time. And what I'm going to do is take a couple of them and dive in and hopefully give you a story to share. So coming back to the big picture I started with, let us just look at 2 fundamental assumptions: time invariance and orthogonality. Time invariance basically means a system we are studying is either not changing in time, either static in time. In most cases, it's time varying. But even if it's time varying, we assume it's stationary with time, like its statistical quality does not change with time, even if the individual attributes do. So what happens when we take away that assumption at 2 different levels? One is the components vary with time, and secondly, not only do they vary with time, the statistical distribution is not stationary. So in that case, can we do something interesting? And then related to that is orthogonality. The different signals of interest or the data of interest, the matrix can be interestingly designed to be incoherent so that we can do precise signal recovery. What we find again and again that the ocean sciences is a very humbling discipline. As we plan our science and we take our algorithms to the ocean and we apply it over data, and a lot of things don't work. And then that was one of my, how shall I say, now I call it my privilege, that it was a learning experience as I went through months of applying very traditional and successful sparse sensing optimization over a lot of our acoustics data at Hui, and it just didn't work. And then I found that the fundamental assumption of orthogonality was so badly violated, it didn't even occur to me. It was way over in that skew, and so new theory had to get developed. So that's why I think shallow water acoustics is kind of the poster child case of an oceanographic problem that is pretty visual but communicates the kind of theoretical challenges and underpinnings we have to deal with. So here what we have is a transmitter and receiver, not that different from, as we are familiar with the cell phone communication style, where we have a direct line from the transmitter to the receiver, and then we have multipath introduced as the signal bounces off different reflective objects and reaches the receiver at different times. So we characterize this multipath effect, using channel estimators, which essentially characterize the channel as there's the direct arrival and then there's a secondary and tertiary arrivals. How is it different due to the ocean surface? The reflections from the bottom, and right now I'm being very simplistic because the bottom itself can be a very interesting paradigm to deal with, but let us say the reflections from the bottom are static. The reflections from the top are due to surface waves, which are highly time varying, and time varying in a way that cannot be modeled by a random walk or modeled by, a Gaussian process or having a uniform distribution, but more by physical processes governed by the ocean. So there is a periodicity, but it's not really a sine wave. There is a lot of complex interaction between acoustic physics and ocean wave physics that happen, and therefore the time varying nature of, I'm going to jump one slide to make it more visual, the time varying nature of the shallow water acoustic channel as a time varying channel itself is very interesting. So what do we have here? We have field data collected from the Space 08 experiment. This was conducted by Jim Preissig, my postdoc supervisor, and all this work in shallow water acoustics is in collaboration with him. And this was conducted in fall 2008 near the Martha's Vineyard Coastal Observatory at Huey at a water depth of 15 meters, a range of 200 meters under moderate wind conditions. Well, we collected data over a lot of other ranges and wind conditions and other parameters. This particular data shows these parameters. And what's interesting to see here, on the x-axis I have time, absolute time in seconds, and for each of these instances looking back, we have the spread of the channel. And by spread of the channel, I literally mean the direct arrival and then the multipath arrivals happening at different times. So if I just look up along a particular point vertically, I see a steady direct arrival. This is coming straight from the transmitter to the receiver. And then we have the secondary arrivals due to the reflections. And what's really interesting to see here is these secondary arrivals, there are two things. One, that they vary a lot with time, and they follow interesting bands. Now, what do these bands really mean physically? So I wrote up a simple simulation model based on wave physics to see if I can actually map these bands to actual things happening in the sea. And so this direct arrival, I aligned them, and here what we have is these bands. This first band, which actually corresponds to a single surface bounce and a combination of bottom bounces. So that means something like this. So one bounce from the bottom, one bounce from the surface, bounce from the bottom back, or maybe one bounce from the surface straight, or maybe one bounce from the bottom. I don't think I have it here. Yeah, one bounce from the surface, one from the bottom back. But the key thing is there's only one bounce from the surface. And I found those get clubbed in the first band, which actually consumes a lot of the energy, and if we do not track it well or account for it well, when we try to design a communication algorithm, we will never hit the right data rates. We will make too much error because of too much interference from these reflections. Now, this tertiary band is actually from multiple surface reflections, and those are highly time varying, and they all nicely again loop together because of multiple reflections from the surface. So that would be more like, I don't think I have an example here, but it would be more like if this bounced and then bounced and then bounced and then bounced. So as we add more bounces, what is going to happen is we have more attenuation with each reflection. So the cumulative effect of this is more spread, but the activity of this is still time varying and spreads over a little bit of larger range. So how is this interesting? This is interesting because, coming to the next picture, if we now just take a Fourier transform in absolute time and look at what we call the delayed Doppler spread, and Doppler here means Doppler introduced by the fluid motion of the waves. We are not considering Doppler due to the boat being towed. So this is purely Doppler introduced by the environment. So what can we say about it, and why is it important? In communications, we use OFDM communications a lot, where we are sending several frequencies and we are trying to detect them. Now in acoustics, because the wavelengths are comparable to the Doppler shifts that can get introduced, or rather the wavelengths are comparable that the resolution we need to do successful communication for OFDM can actually get hosed by this fluid motion and reflection introduced by the waves. Why? Because we see the direct arrival being summarized as one point here around 0, and then we have these clouds of delay Doppler spreads. So what do these clouds mean? It means that the ocean as a channel is introducing its own Doppler shifts to whatever we are transmitting, and therefore there is significant multi-carrier interference introduced by the environment itself that is not stationary, because wave dynamics is hardly ever stationary. It's dependent on a lot of things, and it's highly time varying. And so if we do not have a good way to understand this very significant interference that occurs in lumps, that's the other thing. There are three things. One is it's time varying. Two, the time variance is not stationary. And the three is the interference occurs in lumps, or sparse as we call it, where we have a few significant components but a larger spread, what I call the cloud, across the spectrum. So therefore, if I just use an adaptive least squares type technique that's used so much in, let's say, adaptive beamforming, and just try to find these dynamically, it is going to do a compromise between the high and low values, and therefore it will detect interference where it's not and miss out the really high interference, and therefore create serious data error rates. So what do we do about it? The good news is in the last, I think, 6 or 7 years now, compressive sensing, a pretty established field in signal processing now, has been developed to handle the kind of case where the data occurs in lumps or occurs in spikes. And what people basically do there is design a lot of sparse optimization techniques to find the high values over the low values, and generally do a good job. And in that line, I framed my model like this, where the underwater channel model is given by the observation. I is the current time step, the time in absolute time. And the Doppler effect is introduced as a complex exponential. Gamma L is the Doppler frequency. And we have the input given as x, and we have k delay, so that is how many points here. So we can therefore characterize the channel as the complex coefficients u star, which have to be detected with the knowledge of the input, what Doppler frequencies we wish to sample in. That's, how dense they are, or how much we remove them. It's kind of our choice. And then we have the noise process V, which for simplicity right now I'm putting as Gaussian. So that said, then, can we really characterize it? The interesting question is, we do actually want to put the Doppler frequency sample fairly close, because that's how we can really gather a lot of the wave physics activity. But what that makes is three fundamental challenges, which is why we cannot do a conventional sparse reconstruction and tracking from the compressive sensing theory directly here. So normally, what we would do in sparse sensing is, here is the traditional least square error metric in blue, and typically we would add the L1 norm of what we wish to estimate, and L1 norm is the sum of the absolute values. So what that geometrically means, if this is our data plane, and let's say epsilon is the error around it that we are trying to constrain ourselves into, a least square technique is going to find the point on this cylinder that's closest to this origin. And so it's going to blow up a circle and find the closest point. But as you can see, even in 2 dimensions, that would include both dimensions and therefore make a compromise. What we want to do instead is catch the bundles, catch the lumps. So what we do, what the L1 norm does, is it throws up contours which are like this rhombuses, And as they blow up, where a corner of the rhombus first touches the cylinder is where our solution is. So that means then, where a corner is touching, that is the most likely bundle of coefficients that falls within the error specifications of our data. And therefore, we are forcing a sparse constraint on a solution. So all of this is well and good. And I tried it for 4 months over our space data, and it wasn't working. And then I realized that it wasn't actually me, it was the nature of the problem, because there were, again, 3 fundamental issues that we assume in sparse sensing theory that are getting violated here. First is the C matrix here, which is a combination of our input data and the Doppler spread that we want to sample. This is highly ill-conditioned. And as you can see, the numbers are basically in the range of machine precision. So I'm basically saying that the C matrix typically is not just highly ill-conditioned, it can even become singular, completely singular. And in sparse sensing, we assume C to be incoherent, as in it to have at least as much low rank as you expect sparseness in the system. So let's say if you expect 10% of the entire spread to be significant, then those need to be captured incoherently, and the rank of the C matrix will reflect that. And I can catch me offline on the mathematical proof or gymnastics of it, but basically what we mean here is if the C matrix is singular and it has really low singular values, then the precise reconstruction criteria that we assume in sparse sensing is violated. So that's the first. And then we are optimizing over a complex field, and complex field optimization has been done for least squares, where people would separate things into real and imaginary parts. Some people have done it recently over the L1 norm too, where we just take the absolute value of the real and the absolute value of the imaginary part and then do the same thing. It becomes a problem over reals. For the ocean, that is not interesting to us because we actually want to optimize directly over the complex field, because even the little phase changes induced by the ocean carry very rich, intricate information about the wave dynamics that we wish to capture. So that's the second part, how to do L1 optimization, L1 constrained, L2 optimization over a complex field. And the third is the time-varying nature of view that I've gone over, that is not only just time-varying, it's also non-stationary. So can we do adaptive sparse sensing over a complex field when potentially our C matrix is highly conditioned and we know that precise reconstruction is not feasible? So then what is the question we want to ask? We know that precise reconstruction is not feasible. Does that mean we give up? Or does that mean we try to do the best we can? So therefore, I kind of thought of the problem as a combination of the A, B, and C, where A, B, and C individually are very well addressed in the literature, but when you put them together, what I call the green zone is where there hasn't been much work done. And that is where I went in and I developed a robust and novel tracking algorithm that kind of takes the goodness of the adaptive least square techniques and the goodness of sparse optimization techniques and mix them in an interesting non-convex approach so we can track it robustly. And unfortunately, I cannot get into the exact details of the algorithm in the scope of this talk, but to kind of give a proof of concept that it makes sense, I am going to present what we found when I implemented this algorithm over our data. So what we see here now is the estimated channel response based on the field data we have. And again, we have now the delay is on the x-axis, and we have the value of the channel coefficients on the y-axis. And the lambda parameter essentially is how we weight the two norms. And it is what the lambda parameter really does is it talks about qualitatively, actually quantitatively, if we can pose it that way, what percent of the entire spectrum is actually significant. So the higher we set lambda, like when we set lambda really close to 1, we are essentially doing a least square estimate. And the lower we set lambda, the more we catch only the spikes. And so what we see here now is over the delay spread, as we increase lambda, it captures more and more activity. How much of this activity is real? How do we estimate it? Because, unlike an engineered problem, we do not know the ocean as a channel the day the experimental data was collected. So how we find it is with respect to the prediction error, which is we predict what we want to see next and see how badly we do. And based on that, we found the best solution was given by something like 0.4, which means, yes, it's sparse, but it's not highly sparse. And the interesting thing we also found, and I did not put in more data here, what we found that the lambda parameter over the field data itself is non-stationary. And that is another interesting thing that makes this problem hairy, because all sparse optimization as a regulator parameter, which is by design based on the application at hand. And what we found that yes, whatever value of lambda we choose, we can cast the direct arrival, but the interference from the secondary and tertiary arrivals vary very much based on what is the value of lambda. And the lambda itself, based on the data, actually really varies in a non-stationary way. This is a snapshot in time. At this given snapshot, the right value of lambda was 0.4. But if I were to plot it over time, I would see very high fluctuations. And we can visualize this because, a ship could come through, there'd be a lot of waves, there'd be suddenly a lot of activity, and then things would die down, right? So the sparseness of our system just went from very dense to very sparse. So with that, we compared with what currently exists in the literature. This is the L1 regulated least square technique developed by Stephen Boyd's group in Stanford. Very good algorithm, works for a lot of cases. But in this case, we found because of the highly conditioned nature of the problem, it was not fast enough for our needs. Also, we found that its performance, particularly over the delay Doppler spread, where we are really looking at the spread of the Doppler, the errors were not competitive for our needs. And so that's where we found that our algorithm that we developed specifically for shallow water acoustics was actually really interesting because it gave us a 0.1 dB improvement, which for acoustic communications is actually a big deal because it can really hike up capacity to as much as 50%. And more than that, it made it more than 20 times faster. So this is really the ultimate buy-off because when we are really putting something underwater, complexity is a key issue because we cannot really put expensive hardware that can heat up or have a lot of time to run in a highly time-varying system. So because of this combination, we found that this really worked. And also, now we have developed a technique that can go beyond shallow water acoustics and help compressive sensing and sparse optimization for non-stationary and coherent systems in general. So this is a place where I would again invite comments from colleagues in the field of similar signal processing issues they have run where they are looking at sparse data that could be a non-stationary system. You have singularity issues and how you're dealing with it. And that is why I think the ocean sciences in that way challenges the signal processing, and we develop theory that can spread beyond an oceanographic application. So here, I'm just going to wrap up and say that this is not just the end of the story. There's a lot of continuing work going. One of the things I have not talked about in detail is how long should we wait before we estimate the channel? Because what averaging window we use, how many observations we observe before we say what the channel U is going to influence what the channel U is. And because it's a physical process, it's kind of, like a magnifying glass, which aspect of the time variation do we want to see? Do we really want to see the rapid fluctuations? Do we want to see the more steady fluctuations? And of course, there has been a lot of wavelet theory developed to localize in frequency and time. But here again also is the open problem of what would be a good wavelet to apply in this paradigm. Should we just import what has been tried, or rather let the physics drive the problem? And that is where I have some preliminary work going on, where I used my algorithm over very different averaging windows. And as we expected, the shorter averaging window of 680 milliseconds picked up a lot of the secondary arrival activity right here. And observing over a longer window averaged it out. And it only captured the parts of the activity that is more steady. So based on this actually makes physical sense, because the closer we get to the zero line of the Doppler here, that means those are the slower varying waves. And the further we go, we have more rapid fluctuations. But even then, it doesn't mean that the further we go from the Doppler, we have the more rapid fluctuations. It's more complex than that. Because if the ocean was a completely stationary process, then we could catch the rapid fluctuations over one window effectively. What happens is the rapid fluctuations we found are more centered around different bands of arrivals. And that is where we are trying to develop some targeted techniques that will catch the rapid fluctuations as well as the more steady state variables over like a multi-scale window. And that's research in progress. So I'm going to switch gears and summarize what we have seen so far, that time invariance and orthogonality applied to under shallow water acoustics brought us to a place where we had to examine pretty hard signal processing challenges that are more broadly applicable than shallow water acoustics. So I'm going to look at two other assumptions that get violated, and now from the lens of petroleum forensics. So the assumptions here is linearity and orthogonality. And by petroleum forensics, what do I mean? So what I mean here more specifically is, let's say if we collect an oil sample found in the ocean, and we ask the question, where did it come from? So this is a question that my collaborator, Christopher Reddy, he is a senior marine chemist at HUI and is the person I have been working with intensely on this project. He asked me, and the answer turned out to be quite non-trivial. So it was more in the context of the BP oil spill disaster, where we were asking the question of, if there is another oil spill tomorrow, or let's say if tomorrow we find oil samples found in the ocean, can we do an environmental assessment of what is the long-term impact of an oil spill disaster? But to oil companies, actually, it is also an equally important question, because they like to look at oil wells and try to ask whether they're connected, because it's going to drive billions of dollars of decision about how many times you drill. If they're connected, you drill once and you take really painstaking efforts to make that a safe drill, and it makes the planet happy, it makes the company happy, it saves money, and it saves a lot of money, and at the same time it also helps us understand the planet in terms of its distribution of oil fields. So it's a very interesting and important problem. Now, why is it hard? So I am going to give my little bird's eye overview of gas chromatography for a broader audience, which is what we have here is a comprehensive two-dimensional gas chromatograph. We inject the sample in, and it goes through the primary GC oven, and then it gets separated in the horizontal dimension here that we call the first dimension. And that's how we separate initially a lot of the compounds based on their molecular weight, and depending on how fast they come out. And for each of these compounds that are coming out at a particular time, we pass it through the flame ionization detector, where we get resolution for each of these points in the first dimension along the second dimension. So what we have here is a two-dimensional gas chromatograph for, I believe, the Hopane and Sterin region. And this was given to me by Christopher Reddy and Robert Nelson at Woods Hole Oceanographic Institution. And my task was analyze these two-dimensional GC images and ask the question, can we quantitatively relate two of these images with the question how related they are. It's not a binary question. It's a question of, can we assign a number that we can trust? And I want to iterate that while what I'm going to say forward is developed around gas chromatography, its impact and scope is pretty much anywhere you have a distribution of information that has been spanned over different dimensions looking at different things. It's more an informatics thing where we have data sets and we are asking a question of how related they are. So this can apply to mass spectrometry. It can apply to combination of mass spectrometry and chromatography. It depends upon how the chemists will put their stack up. And then I look at, gigabytes of data or kilobytes of data. But in terms of how my algorithm is going to work through the data is driven by the question rather than the volume of the data. So it's a scalable algorithm, and at the same time, it is an algorithm that is sensitive to the science question being asked. So going forward, I'm going to present the problem a little bit more so we can all visualize it. And this is scoped to the context of the Gulf spill disaster, but again, that's more to give a story to the thought rather than limit the scope. We have the Macondo well, which is the well that had the disaster, and we have the southern Louisiana crude, which is another oil well in the vicinity. And here we have two-dimensional gas chromatographs, and as we can see that they look somewhat similar in their context and texture, but even with their eye we can see that there are certain differences. So the question then is, how well can we separate these differences? Because clearly if we just do a KL difference between them, or if we do a correlation analysis between them, there's a lot of similarity in the texture just because they are both gas chromatography. And then how can we separate that? So traditionally what chemists would do is look at these big higher peaks. So this is the same picture but drawn differently, more three-dimensionally. And chemists would typically look at these distribution of the bigger peaks and look at their relative ratios and come up with an expert opinion on how these are related. And then I started to ask the statistical question of two things. First, what is the information that we are looking for here? And then how can we detect and compare this information in a goal-driven way? So moving forward, what I'm going to present is part of ongoing work that is currently under copyright. We filed our provisional patent, I think, in April. And so I've been advised to put proprietary on all the slides that are IP content just to mark it out to anybody I make a presentation to. So I have to say it. And but at the same time, I'm free to talk about it because we are already covered by our professional. So what I have proposed here in the context of this problem is we want to look at the entire topography. And by entire topography, I do not mean just GC versus two-dimensional GC or two-dimensional GC versus mass spectrometry. By entire topography, I mean the entire data set. And the question I'm asking then is, in this entire data set, given that the chemists typically look at the peak values for the answer, how can I glean information from this two-dimensional image into a feature representation that captures the information and throws away the noise? So what we have here is take each of these points in the horizontal axis, look up in the vertical direction, what we will see is these peaks. Find the exact location of the peaks. For that, I have proposed a gradient-based signal processing approach on how we can exactly separate the peaks, and then store just the peak values along the vertical direction for each of these points. So what I have here is the peaks along the vertical direction all drawn, collapsed for each of these horizontal points. So they are shown as overlapped, but actually I'm not overlapping them in the feature representation. The point of this middle picture is to show that the peaks can be separated, and B, besides the peaks that chemists look at, this is the amount of the minor peaks that get routinely ignored in intricate data interpretation. And so this is the amount of data where that signal processing can glean out and put into the analysis, so we can get a more believable quantitative measure when we compare to chemical samples. So henceforth, I'm just going to focus on the feature representation, which is nothing but all of these peaks represented in their right position. So that's how we preserve order. So just by looking here, we know that what compound we are looking at. And then I'm going to compare these feature representation that I call the topography map between samples. And to go back to the picture I presented earlier, remember that these two images looked kind of similar, and when I put them through the feature representation, these contain the exact same information from this much higher data set. And similarly for this, and now we can even visually see that they look more different, because what I have done is bring out the information, the content that was important, and thrown away, how the peaks rise, variability issues, do they move around a little bit. All of these things typically, are very hairy problems that chemists and chemical analysis have to deal with. But because of the feature representation, we can be immune to all of that and focus pretty much just on the information. So I would say the takeaway from this particular work is pretty much just the visual impact of this slide, where we have the same data just represented in an intelligent way so that they can be separated better. So can we separate it better? Here is some source classification I did based on this approach that I call the topography mapping, and this is a subset of the approach that I call topography map filtering, where I have basically done is I took 20 samples from Chris and Bob, and the blue ones are the ones that relate to the BP spill. The ones marked in green are those that were in the area, so they were closely related sources, much harder to separate using usual chemometric techniques. And the black ones are from all over the place. And the interesting thing is 2, 3, and 4, these 3 samples are standard crude petroleum samples that were run in succession. So they are what I call twins from another family. So even if they should not compare with the BP samples, they should compare very well with themselves. And then what I have is on the left side, without using the topography maps, if I just compare the corresponding images, and I did a basic mean square array distance, which is what you would do as a first principle in signal processing, how much can we separate it. And we see that, yes, the standard samples, look similar to each other. So this is 20 samples compared against themselves, so 20 versus 20. So the diagonal is a sample being compared to itself. So therefore, it should be 0. The more blue it is, the lower the value it is, the more similar it is. And using traditional signal processing, we see that, 6 and 7, which should be really unrelated to each other, and to the BP samples are unrelated, but particularly the blue and the green samples show very little diversity or distinction between themselves. And this is because their images look that similar. They show divergence against, other things like the standard samples, but between themselves, there's not enough dynamic range. And now I put them to the topography map filtering, where I have basically used just a few of these samples to actually, in this case, this is a direct sample-to-sample comparison. There is another part where I train some samples to recognize a given source. This particular matrix is actually just on a sample-to-sample basis, where I am taking a sample and just comparing its raw topography map with no other knowledge against another sample, and the only filter I'm putting in is filtering it by the peak height, by the mean peak height. So what I'm basically saying is look at all the peaks, but if you see a big difference in the peak ratio for a big peak, that should count as more. And if you see a similar divergence for a smaller peak, it probably counts less, but it should be accounted for. So with that, just based on the data, I have the same matrix, and we instantly see that there's a lot more distinction coming out. Like the green samples now really stand out against the BP samples, which, as we expect, are close to each other and to themselves. So this was the proof of concept that got us really excited and got us to really take this work. It is currently at a fairly mature stage, and I would be delighted to talk more about it offline. And looking forward, we have a lot more other results that have evolved since this result was derived, and this was way back, I think, last November. And so the last 4 months has been extremely exciting for us. And this is where I would, zoom back and talk about where I think the approach we have described is more broadly applicable than petroleum forensics. And this is where I am really inviting a lot of feedback from Microsoft and hopefully collaboration interest, because I know that there are a lot of people here who work in human-computer interaction, who work in pattern recognition problems, people who are in video analytics, and what we are essentially trying to, the signal processing problem that I am trying to solve here is if you have two things that look very similar but have idiosyncrasies that are marks of their personality traits, let's say, then can we recognize them using an algorithmic method, and then can we tell them apart? So for example, if we are talking about, instead of doing direct face recognition, we have a camera that is seeing a silhouette of a person coming from a distance, and we want to say, based on this person's walking gait, can we identify the person? Let's say if we have a security camera that has employees coming in, the same 20 employees coming in every day, so we collect a lot of data on how they walk and flash their card and go about their daily business. Besides the obvious things like what they look like, there's a lot of their body language that gets captured in the video. And those are like subtle personality traits that if there was a human guard standing at the door, he could recognize from a distance. That doesn't look like, Dr. Sengupta. She never walks like that. That's probably somebody else trying to dress up like her and could show me a gun, in that sense. And so that's kind of where I'm going with this, that the philosophy I'm bringing in is there is a lot of subtle traits that is there in the data we look at. There's a lot of informatics that gets done, and we can do some targeted signal processing and pattern recognition work, and I'm sure people here already do that, and I would welcome feedback and communication from them and see what we can build together. So with that, I'm going to wrap up and go back again to where we started the story and summarize a little bit so we understand where we want to take the story forward. So the research vision is to expand our scientific understanding of complex physical environments by breaking the barrier of limiting assumptions and signal processing theory. And the interesting applications that have looked at so far for addressing signal processing challenges has been in shallow water acoustics, for adaptive sensing and non-stationary environments. That was the first half of my talk. There is parts I did not talk about, another very related application, but with very different and unique challenges in the same paradigm, is underwater acoustic array processing. And I know that there are excellent array processing work being done here at Microsoft. And I would be very curious whether you run into similar issues when trying to combine spatial diversity and array processing with acoustics, and when you also have to deal with human interaction and speech processing and stuff like that. Then sparse sensing for highly coherent systems. That's where shallow water acoustics was the classic application. I found out the hard way, but feel both humbled and wizened by the process. And this is a bullet where I'm really hoping that somebody will ping me and say, I ran into the same issue in this completely unrelated application, and see what we can build. I think in image processing, probably there would be similar issues that people face. I wouldn't know, because last time I did medical imaging was 2001, but I am very curious to hear about it, because I'm really trying to get the research in a broader paradigm here. Highly correlated signal separation, the classic case I presented was fingerprinting closely related petroleum sources, but this alone itself can be its own book. All my PhD work, which I did not cover here, was separating highly correlated signal that overlap non-linearly. So if you have an amplifier with saturation and you're blowing up your signals through it because you want to pack that many users within the same bandwidth, then after a point it will reach the parts of the S-curve where they will start interfering, but in a non-additive way, and that's highly correlated. Can be separated. And I found that the answer is definitely yes, but depending on how far into the saturation you go, your performance will fall down. But there's a long rope, there's a lot of loose rope between the linear world and the completely saturated world, and that is completely unexploited territory where I found a lot of improvement. And I'd be delighted if somebody comes and finds an application for it that I can actually see that idea implemented in a real product. So lastly, optimization in low signal to noise ratio and nonlinear and non-Gaussian regimes. By that, what I mean is, if we are trying to find signal across a paradigm, that there's a lot of noise, and we want to first find, is there something there? If so, how much? And then the noise itself may not be additive Gaussian, as we always, not always, but often assume. And in that case, can we again detect against the presence of non-Gaussian high ambient noise? A classic case I'd put forth is sonar signal processing, where a lot of clutter can be, non-Rayleigh in nature. A lot of clutter can be due to other species or other things in the environment that is noise to us, but signals by their own right and do not necessarily follow a Gaussian model, but do contribute significantly to the noise. So applications would be, again, fingerprinting across unknown distributions. So how does this relate to the petroleum work I just talked about? What I haven't gone into, and is an aggressive part of my current research, is how are these whole spread of peaks, big and small, related probabilistically to each other? That is, in a sense, an unknown question. Like, what people have studied is take one compound and another, compare their peak ratio, do a histogram across the samples, so we can understand how that ratio itself follows a statistical distribution. But that's a completely separate question from asking, here's this entire spread of peaks. If you think of it as marbles rolled along a floor, how are they statistically related to each other? And does that carry the footprint of a particular source? And we feel that answer is yes, and it's a very important question. And I have some very exciting results on that is outside the scope of this talk. But I see that as having very broad applicability. And this is, again, where non-Gaussian is a very important word, because here we are not really talking about noise, but what we are talking about is the way these peaks would be related to each other may not follow a jointly Gaussian model. Anytime we say jointly Gaussian, we are assuming some kind of a linear model, that random statistical processes will add on, the central limit theorem will be valid, and so therefore we can write our favorite PDF and get our answers. And of course, probability at the end of the day, a mathematical formula is nothing more than a formula. What breathes fire into it is when the formula actually becomes a realistic measure of the scientific problem we want to study. So this is again where I'm pushing to take a non-Gaussian outlook at the petroleum fingerprinting problem as a statistical problem. And that again relates to, I already went over non-Rayleigh scatterers in sonar, how we characterize and classify them, detecting a source against a severe backscatter. There is also a lot of work currently being done at HUI by people across campus on underwater imaging and optics and dealing with non-Gaussian scatter. So I would also invite participation with the HUI community where we, as part of our research life, look at these problems a lot. So with that, I'm going to conclude my talk and leave the forum open to feedback and questions and new problems, and hope that even though I went pretty technical on two applications, that you all understand my talk is more intended to put signal processing into this big picture scenario where all the problems, even if they look very different, are ultimately related, and they're often related through unique and extremely similar challenges. So the more people from very diverse fields come close to work on similar challenges, the better science and engineering solutions we can produce. So with that, I will acknowledge Jim Preissig, my postdoc advisor and principal collaborator in shallow water acoustics, Christopher Reddy, my principal collaborator and senior scientist on the petroleum work, and Jim Lynch, senior scientist at HUI, who has been a mentor and really helped me see the light in underwater acoustics with ocean physics in the equation. And thank you again, Dr. Fatland, for the opportunity to talk.
Thank you.
Welcome.